Hello, my name is Ben Zimmer from Enable Training and Consulting, and welcome to the next installment of the LV Mastery TipJar. In this installment, we're going to talk about the FRC Robotics Competition framework again, and we're going to talk about sending data around. Many of you may have noticed that putting all of your code into the Tele-Op.vi can have a negative effect, which is that the Tele-Op.vi doesn't run particularly fast. There's an awful lot of communication with the driver station that goes on in that VI, and if you're performing tasks such as checking for limit switches, you may very well find that the delays are too great to allow your robot to function properly. So we're going to talk about some of the other approaches you can use to have high priority loops, which lends naturally to the question how you send data around your code. So let's begin where we left off the previous installment, having just created a state machine code to drive a theoretical lifting mechanism. So if we open up our robot main, let's just review where we placed all that code. In the begin step, we opened up 3 digital inputs and a motor controller and wired all of them into a type def which we created specifically for our lifter. That lifter type def contained the device references for the hardware, as well as an internal state, an internal delay timer to keep track of when to move to the next state, as well as keeping track of the output values, the current motor speed, limit switch values, and the ball sensor value. So after hooking all that up in the begin VI, we then went into TeleOp and created a new sub-VI called the lifter sub-VI. So that lifter sub-VI, as its input, took that type def, which we just created. As its output, gave an updated value of that type def, which then got bundled into the robot data. And of course, when we review the robot data main, all the data in that type def goes into a shift register, so it's available loop after loop after loop. We also created a very quick debugging dashboard, which is simply a sub-VI which unbundles the important information from that type def. Just puts it into some front panel controls so we can monitor it very easily without having to drive and drill down into the sub-VI. So let's review what the problem is. This particular code we created, if you remember how it works, it's a state machine which essentially automates a lifting mechanism. The mechanism moves down to the bottom and waits for a ball to come into the field of a sensor. As soon as that's red, there's a delay, after which point the lifter goes up until it hits a limit switch. When it hits the upper limit switch, it immediately comes down until it hits the lower limit switch. Then it goes back into waiting for a ball. We coded that up in some detail in the previous installment, so I'm not going to review this code at all, except to point out one problem. Depending on the nature of this theoretical lifting mechanism, it's possible that that limit switch, either the upper or the lower, is extremely important. It's possible that if the motor doesn't stop immediately on seeing that limit switch, that physical damage can occur. So it's essential that the limit switch be monitored as quickly as possible. Well, there's a lot of stuff going on in the Tele-Op.vi. We're reading the joystick values, we're doing an arcade drive. In fact, if you close Tele-Op, we see that there's other stuff inside this main loop. There's the dashboard communication, there's communicating with the driver station to determine the robot mode, there's our debug dashboard. There's a lot of stuff going on in this while loop. And for those of you who have done testing, you may have actually observed that the time at which the Tele-Op runs is actually variable. That sometimes the delay between Tele-Op executions is as low as 5 or 10 milliseconds, and sometimes it's as long as 200 milliseconds. So if it takes on the order of 1/4 of a second for your motor to stop when a limit switch is tripped, that could mean permanent damage to your robot. The end result of this whole thing is that it's not good to have time-critical information be handled in your Tele-Op case. And that's why there's a VI here called time tasks, which runs completely in parallel to the loop which contains the Tele-Op. All of your time-critical periodic functions, such as control loops, should be monitored externally to the Tele-Op. So what we're going to do in this exercise is take that sub-VI which we created in the previous exercise to drive that mechanical lifter, take it out of Tele-Op, and actually turn it into a VI which we can run right at the root of robot main, so that it will have deterministic, accurate, and fast timing. Let's begin with the obvious approach. We'll open up Tele-Op, we'll go to the code, we're going to cut our sub-VI, we're going to remove the bundle by name, remove all evidence that we were dealing with that type def from our Tele-Op.vi, and we're going to paste our sub-vi into the root of robot main. So let's take another quick look at this lifter sub-vi. Well, the first thing you'll notice here is that this sub-vi does not have a loop. Essentially, this sub-vi was designed originally to run within the Tele-Op.vi, which runs over and over and over again. So as it is, this sub-vi will not work for this application. We must put a while loop here. So our natural inclination, just make a little bit of room over here, a little bit of room over here. Put down a while loop. Make sure we encapsulate all the code. And we need to hook up our condition terminal. Well, if we take a look at the robot main VI, take a look at our time tasks, VI which we were given, we see here that each of these loops has been programmed to run forever. And each of them has a fixed delay inside. So why don't we copy that code? We're going to take the same approach with our sub-vi. Just paste that inside. Wire our false, which means it will never stop, and put 10 milliseconds as our delay. Depending on the importance of your VI, you can choose that to be 10, you can choose that to be 1, or you could choose that to be 100. Of course, anything in between. We're almost there in terms of what we need to do to make this VI work, but there's one critical element missing. Remember that this state needs to be remembered from loop to loop to loop. So it's extremely important that we make sure that we have a shift register into which the value of our cluster gets passed over and over and over again. And the other really important item is to make sure that we wire up the parameters which we initialized in the begin VI. Let's review inside the begin VI all of the data which we initialized, the opening of the 3 digital inputs and the motor. All that information is placed in the lifter type def. But that lifter type def is actually inside the robot data. So instead of having the lifter type def as the input here, we're going to modify this so that it takes all of the robot data in. So we'll open up our sub-vi, delete the lifter type def in, go to our Project Explorer, type defs, and just drag our robot data right onto the front panel here. Then we edit to show connector and make sure that gets wired in here. And then wired in here. So now we've ensured that the robot data which we've initialized in the begin VI gets wired into our lifter sub-vi. And naturally, we still need to use an unbundle by name to extract from that just the lifter information. Now you may ask, why didn't we just hook up just the lifter? Why didn't we pull it out from the robot main here? Or why didn't we bring it out through a separate output of the begin VI? In this particular case, that would have been fine. But envision a situation where this sub-vi needs to know information about some of the other parameters. Well, the benefit of doing this is that if we wanted to, we could have access to the watchdog device ref, or the joystick device ref, or any of the other parameters which we have placed in the robot data. In this case, all we care about is the lifter, but it's going to make your life easier to always use this robot data and just extract the subtype def that you need. So just to review, we've taken the sub-vi which we created in the last exercise out of TeleOp, we've put it at the root of the robot main so that it's going to run in parallel to all the other activities instead of having to wait for all the other stuff sitting inside this loop. We've connected up